rotational volume or volume of revolution. I'm going to take this function, y equals the square root of x plus 2, and I want to take the area that is created between that function and the horizontal line y equals 2, and imagine that as like a paddle, that two-dimensional space. And let's say I'm doing that up to where x is 4, so from 0 to 4. And I'm rotating this around the line y equals 1. So y equals 1 is my axis of rotation. So stop the video and try to sketch what you think this solid would look like after I take this area and I rotate it like a paddle around that line y equals 1. Did you get something like this? So it's kind of like a rounded out cone, but with an empty hole in the middle, with a cylindrical hole in the middle. Well, how do you think we're going to find the volume of this interesting looking thing? Sure, we're going to draw a cross section, and again the cross section always has to be perpendicular to the axis of rotation. And I'm going to try to analyze what that cross section looks like. So to find the volume of this whole thing, I'm going to have to find the volume of each one of those cross sections. Well, what does that cross section look like? It's a washer. It's a washer. It's a wafer or a disc, but with a hole in the middle. There's a hole in my washer, dear Liza, dear Liza. There's a hole in there. So to find the area of that washer, I am going to have to find the shaded area. Now we know how to find the shaded area. It's the big circle minus the little circle. That's going to give me my shaded area, right? So it's going to be pi times the big radius squared minus pi times the little radius squared. The big radius being that thing and the little radius being that thing. Okay? I should really just draw it like this though, because otherwise that's going to be confusing. So let's look in the context here. So this big radius, is from the function y equals the square root of x plus 2 all the way down to the horizontal line, y equals 1. That's what I rotated around. Well, how far is that? What's that radius? What's that distance? Sure, it's just the top curve minus the bottom curve. So for us, that's going to be pi times the top curve, which was the square root of x plus 2, minus the bottom curve, which is 1. Pi r squared, so I need a square there. Okay, minus, now my little circle here, that radius is just from the top minus the bottom, y equals 2 to y equals 1, that's just 1. So that's not bad. Pi times 1 squared. This is going to give me the area of my washer, the area of that shaded region. So let's see, I can simplify this a little bit. This is going to be the square root of x plus 1 quantity squared minus pi. That is the area of each one of these washers. Now, of course, to find volume, I want to turn that area into a volume. And the way I do that is just realizing, that washer has a thickness of dx. So to turn this into the volume of each washer, probably can't see this. Let's scoot this up. It's going to be this whole shebang times dx. Okay? And now, you guessed it, to find the volume of this whole solid, we're going to integrate. we're going to add up the volumes of each one of those infinite many washers from 0 to 4. Let's see what that's going to look like. So here I go. The volume is going to be the integral from 0 to 4 of, let's see, I had pi times the square root of x plus 1, quantity squared. There's the area of the big circle minus the area of the little circle, dx. So here's the volume of each individual little cross section, and I'm adding up the infinite number of cross sections from 0 to 4. Now usually what we do in this instance is we factor out that pi. It just makes the math easier. So lots of times you'll see it written like this right here. Okay? And we can just put that in our calculator and we should get something close to 58.643 cubic units. Okay. There we go. That seems reasonable, I think, as an answer for the volume of that. So in a general way, when you're finding the volume of a rotational solid, where each cross piece is a washer, right? Kind of the way to think about it is you can factor out that pi, of course. The integral from a to b, whatever your interval is, of the big circle area, so that's pi r squared, minus the little circle area squared, pi r squared, all with respect to x, or if we're doing it with respect to y, that would be dy. So to find the volume of a three-dimensional rotational solid where each cross section is a perfect washer, this is kind of the setup. The area of the big circle minus the area of the little circle. You're turning those circular cross sections into volumes, but with a thickness, and then you're adding up an infinite number of them. I think these are kind of fun.